Hello everyone, welcome to my video series about probability models in DNA sequence evolution. My name is Tagore Zhao, and today we will be going over Wright Fisher model with mutation and heterozygosity, or if you're familiar with its complement, homozygosity. Let's do a quick recap of the Wright Fisher model. It is a homogeneously mixing population of constant size with mutation with neutral mutation, meaning that the mutation itself does not change the fitness of a single allele. And if we model it in a Markov chain, let xn be the number of type big A allele in the nth generation. Remember, there we only have two types of allele in our previous setting, capital A and small a. And it is clear that xn given xn minus 1 equals to j is binomially distributed. And thanks for my friend Alex for correcting me on this abuse of notation. And we proved the kind of like a toy-like martingale probability that the expectation of xn remains the same regardless of the generation. And we also talk about the exit distribution, the stopping time, or the fixation time. The book uses the term fixation time, and we will be using this term throughout the course. And it is the minimum amount of time we need to reach the absorbing state of this Markov chain. There are two absorbing states in this Markov chain. One is 0, the other is 2n, meaning that we only have all capital A or all small a. And we proved this. We've proved the probability of reaching to 2n, eventually ending up in 2n, given an initial state, is equals to I over 2n, which is the initial frequency of the type capital A allele. So, and we proved this using the martingale property. So let's kind of generalize this notion because now we only have two different alleles. What if we have multiple different alleles? For example, if we have, okay, let's not use E, let's use just regular capital E so that we don't confuse it with expectation. So what do we have like E1 to EK type of alleles? The reason why I use it here is kind of like different types of alleles are kind of a basis for constructing this set. So I'll use E1 to EK. And it is very easy. So it is actually simply a multinomial sampling instead of a binomial sampling. So I'll just write down the probability distribution, and you can check for yourself. This is actually very simple. That beta 1, beta k corresponds to the number for each type of allele. This is alpha 1 to alpha k. And we're sampling from bit 1 to the dot bit k and alpha 1. Oh, this is actually 2n. Remember, we have n individual. Each individual is which is called a diploid, has 2n allele. For simplicity, we only think about the 2n allele. So this is actually 2n. But when we're referring to n individual, you should be able to understand what it means by n individual and 2n allele. They're the same thing. Okay, beta k here. So this is just simply a binomial distribution. So let's remind you about the general process of generating this Wright Fisher model, going from generation to generation. So we first have 2n alleles in the generation, and then these 2n alleles reproduce, which is an individual. I marked it here. And the next generation is formed by sampling n offsprings, which is also 2n alleles. Meaning, remember, we have constant population size. I should use the same unit, but I'm sorry. We'll be sampling n offsprings from the parent population. And the mutation can occur during reproduction with probability mu per individual per generation. So this is the definition of mutation rate in the discrete case. It's just the mutation probability. And we haven't really talked about the mutation yet. Let me give you a simple example. What does a mutation looks like? A mutation is simply a change of the type of an allele For example, if we are only considering there are two types of allele, capital A and small a. We sample, for example, we start with a generation 2n and we sample a capital A from the previous generation. And this capital A has maybe 50% of probability of mutation, meaning that the capital A will be transformed into small a. That although we sample a capital A from the previous generation, it eventually becomes a small a in the next generation. And this is called a mutation. And this is kind of like the simplest form of mutation where we only have a finite, actually only have two different type of alleles, and they have like equal probability of mutation. So this is actually not interesting, and if you're interested in the probability distribution of this kind of simple Wright Fisher model with a simple mutation, this is actually a neutral mutation, and you can just you can look it up, or you can. I think it's really easy to derive. So an interesting question would be, assuming the mutations are independent, what is the mutation rate occurred to the population at a generation? Remember, we have a mutation rate occur to an individual at mu. Remember, mu per individual per generation. Now, what is the mutation rate for the entire population at a generation? I believe audiences smart like you already figured out. It's actually, I'll just write it down. If you don't know, you can pause and think about a little bit. And the answer is actually just 2 and mu. Why? Because for each generation, we have 2 alleles in the population, and each individual has a probability of mu of mutating. Therefore, the mutation rate to the entire population is just 2n times mu. So another question that is asked is that what is the rate of fixation of neutral mutations in a population of size n, or 2n alleles? I know this might be confusing, meaning that what is the rate of fixation of neutral mutations? We need to really understand what is the fixation of neutral mutation means. So the rate of fixation of neutral mutation is actually the number of neutral mutations that become fixed in a generation per unit time in a population. Sorry. And this unit time in the discrete case is just per generation. And after we define this is actually very easy to see. Since the mutations are independent, we actually just need to calculate the number of new mutation introduced per generation. Remember, in this setting of the model, we assume all mutations to be neutral mutation in order for the Wright Fisher model to hold. So we will not keep saying neutral mutation. And just to remind you, a neutral mutation is that this mutation does not change the thickness of a single allele. And times the probability of each new mutation introduced. But we already know all these things. The number of new mutations introduced per generation is, we have already calculated, 2 mu, right? The number of population times the probability of individual a mutation occur to each individual in the generation, right? Times what is the probability that each new mutation introduced? Probability that each new mutation introduced. It is actually equal to the frequency, right? Initial frequency, each new mutation is just 1, right? Over 2n, right? Remember, we calculate, this is just probability. This is the same as probability of x0 equals to I, and x tau is actually equal to, we have x tau here, right? And therefore, we actually get mu. The rate of fixation of neutral mutation in a population of size n is actually just mu. So this is actually the simple Wright Fisher model with mutation explained. And we will keep this model in mind, and we will continue to talk about some other measurements. So now we are looking at a kind of a forward direction. We know, okay, if we start with the initial state, the population's constant, and we know how do we sample from the previous generation to generate the next generation. We know the probability distribution generating process. And there are some other things that we want to know concerning the reality, right? For example, if we're given a generation, like a specific generation, we want to know how diverse is the generation, like the diversity of type of ions. How many, like, for example, we only have two different type of ions, capital A and small a. In generation maybe n plus one, do we have like majority of them being big A, or do we have like equal probability, or if we have multiple, are they splitting equally, or are they dominated by the majority type of IO, right? So statistics or summary statistics that measures is called heterozygosity. Heterozygosity here, or homozygosity in which is its complement. So the definition of heterozygosity I write down here. It is the probability that two copies of the locus chosen without replacement, here remember, without replacement at time n are different. So let me just write down the definition of this heterozygosity in mathematical form, which is, I think, is easier to understand. So we're still using the xn defined as before. For example, we have xn number of big A and 1 minus xn number, 2n minus xn number of small a, right? So if we have two copies of locus chosen and they're different, meaning that we have to choose, we have to have a big A and a small a, right? The two choices we make must be different. So we either first choose the big A, then the small a, or we first choose the small a and then the big A. But they're probably as actually equal, right? They are kind of like a symmetric case of each other. So we can actually write first 2 here. And what is the probability of first choosing big A? It is xn over 2n, right? What is the probability of choosing a small a? Remember here, we do not have replacement, okay? Now the generation, the total number of generation, we already select the big A outside of the population here. This population becomes 2n minus 1. And what is the probability of choosing the small a in this case? It is 2n minus 1, which is the total number of population for right now after we choose the big A, pull big A out, minus xn minus 1. Right? Because we have minus 1 number of big A. And if we simplify it, it's actually equals to 2xn times 2n minus xn over 2 minus 2 minus 1. Okay, so you can simplify, you can cancel out the 2 here. Okay, so and the homozygosity, here we write Fn is simply just 1 minus the heterozygosity. It is the probability that two copies of the locus chosen without replacement at time n are the same. So after we define this new summary statistics, a common question asked is what is its expected? What is its expectation? What is the average heterozygosity in a generation N? Can we derive like a formula for it? A common proof. Most people will just wrap it up, wrap up the statistics here with the expectation and try to figure out the accent outside and because we know kind of like the expectation of accent is always equal to its initial state, and then we try to like do kind of a arithmetic to calculate. But Professor Druid actually provides a very interesting proof in the book. So we will go over that one. So, an interesting fact. This is also actually a martingale, if I didn't remember it wrong. Okay, so a proof is, okay, let's look at this graph. So we now denote these horizontal lines as the generation. At top is the zeroth generation, is the initial generation. And as we move forward, we already talk about when we talk about the probability distribution of the next generation, given previous generation, we're talking about forward direction, which is going from up that down from zero to the nth generation. But now we're looking backwards. We let xi0 denote the I here is the index of I. Of index of a specific I. If we have like 2n I, we have like indexing from 1 to 2n, right? 0 here denotes like we start from n. Here is the nth generation, right? We begin with the nth generation, and we pick some I indexed by I when we call it x0 subscript I, right? And we want to know, okay, who's the parent? Remember, we sample the nth generation from the n-1 generation, right? So if we have one IO in the nth generation, we must be able to trace back to its ancestors, right? To its father, grandfather, mother, grandmother, and stuff like that. We must be able to trace all the way back. It has to exist in the previous generation in order for it to be chosen in the next generation. So we can go all the way down. Xi1 is the father of Xi0 in the n-1 generation, and then we can choose his grandfather, and then grandfather, and grand until the like the common ancestor at the 0th generation, the most like perceived like guy up there, Xi, which is Xin here. You can see. Okay, so what does this kind of a graph looks like? If we select, for example, 2. Okay, I already draw this graph to save you some time. So if we have like 2x10 and x20, which is just any two aisles selected at the nth generation, and we trace back, okay, this guy has his father as x11, and this x20 has his father as x21, and then we can trace all the way back to x1 and to x2n and x2n. So we know the entire kind of lineage of this aisle, how this aisle like being passed down all the way to the nth generation. So let's think about a general case. Okay, so if we have n here is greater than or equal to, you will know why I write it in like the vertical way. It actually helps you to understand, because this is the when I'm labeling, for example, x0n is actually at the 0th generation. So this is a confusing part. That's why I write n here at the top. It's saying x0n. This n is corresponding to the the aisle, not the generation. It's actually the inverse of generation. And then we can go all the way to this. Remember, this is the generation, right? This is the generation. Let's just call it gen. Okay, gen, and this is the aisles. I cannot always. I can't really like spell it out correctly all the time. So forgive me. So this is the aisles, the index for the generation of aisles, and this is at the actual generation. We starting from 0, go all the way to n minus 1, minus 2, and then go all the way to n, right? 0, 1, 2 to n minus m, and go to all the way to n. Okay, so let's say at some generation m, right? At some generation m, this is greater than 0, this is, okay, at some generation m, and what happens if x1m equals x2m? Remember, x1 and x2 are two different aisles, or two aisles that are indexed differently. Okay, we kind of like two friends in the generation want to know. Okay, and the m here indicates it's kind of a generation. It is at the n minus m generation, meaning that they are the if the numbers are the same, then they're from the same generation. If they are the same, then for example, they're all big A or they're all small a, what do we know about its parent? Or what do we know about its parent at some previous generation? They must be the same, right? Because remember, in the Wright Fisher model, we're going from 0 to n, we're going forward. When we sample these aisles from the previous generation, they make exact copy of themselves to the next generation. So if in x1m, x2m equals, if x1m equals x2m, that means, let me write a here. That means x1 m minus 1 must be equals to x1 m minus 1, right? And we can all do kind of like induction. We can all the way trace back to L, which is somewhere in between N and M, that x1L is equal to x2L. Okay, now we know kind of the relation between the children and its parents or its ancestors. So what happens if x1m does not equals to x2m, right? Meaning that its parents cannot be the same, right? We cannot have like x1m having the same parents and x2m having the same parents, and then just having their children are the same, or if we have like the children are different but their parents are the same. This is impossible in the Wright Fisher model, right? So what is the probability of having this happens given x1m does not equals to x2m? What is the probability that their parents are different? It's actually, we know if we going forward we want to have exact same children, right? Meaning that we sample the same parent. We would have the probability of going this way is 1 over 2n, right? We first sample 1, and we for the next sampling of this of the second children, it must be the same aisle that in the previous generation. So it is 1 over the entire previous generations, which is 1 over 2n. But for if it's different, that means we are 1 minus 2n. 1 minus 1 over 2n, right? Meaning 1 minus the probability that their parents are the same. So let's go backwards. This is 1 minus 1 over 2n. And we guess, where do we reach? We reach x1 minus 1 does not equal to x2 m minus 1. And we keep iterating, right? We have to find, okay, this we can still do the kind of induction step here. And it is what happens at the initial generation, x1n cannot equals to x2n. But what is the probability of this happening? Remember, if we go one step backward, the probability of having different parents is 1 minus 1 over 2n. 1 minus the probability that we have two identical parents. But if we keep iterating backwards, it's actually from all the way from 0 to n, we iterate n times. So the probability of going all the way backwards is actually 1 over 2n over n, right? To the nth power. So, so here, if we have x1m equals to x2m, then x1l must equal to x2l, given l is greater than m. So in order for x1n to equal to x2n, we need to start from the zero and iterate n times backwards. None of the intermediate step can be the same. None of the intermediate step can have like this. Any parents cannot be the same that we are on that is on the lineage. So this gives us the probability of 1 minus 2n to the nth power here. So what happens at time 0? We're just randomly selecting two aisles there, right? Like at the bottom here, we're just randomly selecting two aisles. And this way gives us the initial expectation. So what is the expectation at the nth generation for heterozygosity? It is the initial expectation times 1 over 1 minus 2n to the nth power. So, and this concludes the proof. So sometimes we will see a little, if you have already seen this before, say, hey, this is not how it's defined. We define it with replacement. So this is actually a more common version of heterozygosity. But the book write the previous version because, well, probably Professor Drew would really want to show this kind of a proof, like non-conventional proof of expectation. So this is actually very easy. You see that it's just like instead of having 2n minus 1, meaning that we don't have replacement, now we just have 2n at the denominator, and the above is also 2n minus x0. And this is actually equals to 2n minus 1 over 2n. Oh, this is actually, I think this is 2n. Yeah. All right, and this is h0 and the expectation of xn is actually the same. But remember, this proof does not work the same as the previous one because we use that the probability of having different parents going backwards is 1 minus 1 over 2n, right? Okay, so I think this concludes the course today, and the next time we will be talking about Kingsman coalescence. All right, see you next time.